Dear students, now we are going to learn the structural elucidation of glucose. Glucose has got linear as well as cyclic structure. Now we are going to learn how the linear structure of glucose is arrived at. From the elemental analysis and molecular weight determination, the molecular formula of glucose is found to be C6H12O6. That is, there are 6 carbon atoms and 12 hydrogen atoms and 6 oxygen atoms. Now we are going to find out how all the 6 carbon atoms are arranged, whether they are arranged linearly or do they have any branched chain structure, or the oxygen from 6 oxygen atoms, what are the functional groups present in glucose. The following facts lead to the open chain structure of glucose. Glucose, on treatment with hydriodic and phosphorus, it undergoes a drastic reduction to give N-hexane as the product. We know that N-hexane has got 6 carbon atoms and they are linearly connected. They have got a straight chain, open chain structure. From this we can conclude that glucose has got a linear or straight chain structure. When dissolved in water, glucose forms a neutral solution which indicates glucose is neither acidic nor basic, that is, doesn't have a carboxylic acid group, acidic group. Then, when treated with the hydroxylamine, glucose forms monooxide, and with the hydrogen cyanide, glucose forms glucose cyanohydrin. These two reactions are characteristic reactions of a carbonyl group, which may be an aldehyde or a keto group. Therefore, now we have to find out whether an aldehyde group or a keto group is present in glucose. For that, when we have added bromine water to glucose. Bromine water is a mild oxidizing agent. We know that only aldehydes can be oxidized by mild oxidizing agents. When glucose is treated with bromine water, glucose gets oxidized to gluconic acid, which indicates the presence of aldehyde group. We know that only a aldehyde group can be oxidized to acid having the same number of carbon atoms. When this gluconic acid is treated with a strong oxidizing agent, concentrated nitric acid, we get a glucoric acid, a dicarboxylic acid. Similarly, when Tollens reagent, it is also a mild oxidizing agent, is added to glucose, glucose reduces Tollens reagent to a black silver mirror and gets itself oxidized to ammonium gluconate. This confirms the presence of aldehyde group. Similarly, when Fehling solution is added, we get a red cuprous oxide. This reaction also confirms the presence of aldehyde group. Next, we have to find out the remaining oxygen atoms, which functional group is present. For that, when acetic acid anhydride is added, glucose forms a stable glucose pentaacetate derivative. We know that only the hydroxyl groups on treatment with acetic anhydride give rise to acetate derivative. If one hydroxyl group is present, then monoacetate will be formed. Since glucose forms a pentaacetate, we can know that there are 5 hydroxyl groups are present. Since we are getting a stable product, we know that all the 5 hydroxyl groups are attached to different carbon atoms. If 2 hydroxyl groups are attached to same carbon atom, then that compound becomes unstable and they try to lose water molecule. Same glucose on reduction followed by acetic anhydride treatment gives glucose hexaacetate as a stable product. This also confirms the presence of 5 hydroxyl group. Then on treatment with concentrated nitric acid, it is a strong oxidizing agent. Glucose is oxidized to a dicarboxylic acid, a glucoric acid. This reaction confirms the presence of aldehyde group and also a primary hydroxyl group. We know that only the primary hydroxyl group can be oxidized to acid. From the above evidences, we can conclude that glucose contains one aldehyde group and 5 hydroxyl groups. Out of the 5 hydroxyl groups, 1 hydroxyl group is a primary hydroxyl group and 4 hydroxyl groups are secondary hydroxyl groups and can be represented like this way. That is the terminal group CHO and another one primary hydroxyl group. The middle carbon atoms are asymmetric carbon atoms and each middle carbon atom carries 1 hydrogen and 1 hydroxyl group. To find out, using the structure, we can explain the above reactions. That is, say CHO, CHOH 4 times the middle carbon atoms, then end CH2OH. When it is treated with hydriodic acid and phosphorus, we get N-hexane, and with hydroxylamine, glucose monoxide, with hydrogen cyanide, cyanohydrin, which on hydrolysis gives N-heptanoic acid. With bromine water, we get gluconic acid. With the concentrated nitric acid, we get glucoric acid. With the tolerance reagent, black silver mirror and ammonium gluconate. And with acetic anhydride, glucose pentacetate. And on reduction followed by acetic anhydride, we get glucose hexaacetate. Thus, using this structure, we can explain all the above reactions satisfactorily. And then, the open chain structure of glucose is further confirmed by the fact that glucose consumes 5 moles of periodic acid, forming 5 moles of formic acid and 1 mole of formaldehyde via the oxidative cleavage of vicinal hydroxyl groups. Then, to find, since there are 4 asymmetric carbon atoms, we have to find out the configuration. Glucose contains 4 asymmetric carbon atoms and hence 16 stereoisomeric structures, 2 to the power 4, 16 stereoisomeric structures, that is 8 pairs of enantiomers are possible, and we have to find out which structure corresponds to glucose. Fischer assigned the following configuration for naturally occurring glucose, in which the 5th carbon atom, that is carbon attached to the primary hydroxyl group, okay, carbon having primary hydroxyl group. No? Hydrogen is on the left hand side, hydroxyl group is on the right hand side. This configuration corresponds to D configuration. Since the above configuration of glucose resembles D configuration, it is said to be D-glucose. Fischer arrived at this configuration by synthesizing D-glucose and D-mannose from D-arabinose by Kiliani-Fischer synthesis, and also L-gulose from D-glucose by chemically interchanging CHO and CH2OH group, that is the terminal groups of D-glucose, and rotating through 180 degree upside down. Thus, finally, we can arrive at this configuration for linear structure of glucose, in which the first carbon atom CHO terminal group, second carbon atom hydrogen on